Hello. For our project, we have investigated various optimization methods for motion planning in legged robots. For this project, we investigate two methods of optimization. First, we look at a non-convex optimization, which allows for the optimization to take the full center of mass dynamics into account. However, as will be discussed later, non-convexity means we must predefine the robot's gait. Our second method uses mixed integer quadratic optimization. Here, we must use an approximation of the nonlinear elements of the robot's dynamics. However, the computational guarantees of a quadratic program allow us to add mixed integer variables into the optimization, thus allowing us to optimize over the gait sequence directly.
To start off, let's cover the nonlinear program formulation. In this algorithm, we're provided with a mode sequence, that is, when each of the robot's legs are in contact with the ground. The nonlinear program solver then tries to generate a feasible trajectory for the robot and its joints in order to have it get to its destination while obeying both the laws of physics and the aforementioned mode sequence. We use a simplified model of dynamics, known as centroidal dynamics, wherein we only consider the position and rotation of the robot of and about the center of mass. These quantities evolve according to the forces and torques the robot's limbs apply on its main body. Note that computing torques via cross product is generally nonlinear. Additionally, we also add the following constraints. 1. When the mode sequence says a leg is in stance, it's gotta touch the ground and thus is able to leverage static friction to generate forces on the body. Secondly, the robot must stop and start in the same state, minus the x value, so we can loop the generated angles to have the robot walk even further. Third, robot kinematics must be obeyed. This is also nonlinear. Fourth, the time horizon being considered is divided up into n knot points, each not too close/far apart. These knot points are when each leg is specified as being in stance or not in the mode sequence. Fifth and finally, task-specific constraints are needed, like specifying an endpoint for where the robot should go. Aside from these constraints, we also have a quadratic cost punishing high deviations from the robot's default pose. We do not put a cost on the robot's x position or x velocity, as we want it to be moving forward. Altogether, we were able to get the robot to walk and run by using these two mode sequences. In the running case, there's a point in time when neither leg is in stance. This results in a distinct aerial phase, which characterizes running. A final video of the two gaits can be seen here. Now, Alex will discuss the MIQP formulation of the problem.
We were not able to implement the MIQP formulation on the little dog, and we won't go into as much detail discussing the optimization. However, we will point out two major aspects of the MIQP model to illustrate the important distinctions with respect to the non-convex method. First, the exact torque dynamics of the little dog are bilinear, or the product of two decision variables. This nonlinearity cannot be solved by a quadratic program, and thus one can make a conservative approximation of the dynamics using the McCormick envelope. Here you can see on the left the true shape of these constraints, and on the right is the envelope approximating the dynamics. While this approximation is okay, with mixed integer elements we can make it better. Essentially, one can define variations in the envelope in different regions of the bilinear space in order to hug the real dynamics and obtain a less conservative but still true approximation of the constraints, as you can see here. As we add more regions, we have more exact approximations of the dynamics. The second major difference involves optimizing over the gait sequence. This difference uses mixed integer elements to decide whether an end effector should be in contact with the ground at each time step. Now we can apply optimization over more kinds of terrain without designing an entirely new gait sequence for the trajectory. With that in mind, we can take a step back for a second and consider what the comparison of these two methods tells us. Ultimately, that trade-offs exist within optimization formulations, whether between exact dynamics versus computational guarantees, or a hand-designed gait versus a generalized gait planner. Our modern methods of optimization require us to always choose a set of trade-offs appropriate for a particular goal. Thank you.